Alright, in this exercise we're going to go ahead and we're going to look at designing a valve system. We have some cooling fluid that's going to be regulated by a valve. We have this delta P of our pump, so the pressure difference of our pump. Really remember, pumps they change pressure, not some flow. So it's going to be equal to 100 bar. The cooling fluid also has a specific gravity of 1.1. As a first step, we're going to characterize the valve without the system pressure drop. In a second system, we'll incorporate some system as well. And we'll determine the best valve trim for a linear relationship between valve lift and flow for the installed valve. So the first part is valve characterization. So here we have a pump plus a valve. We derive a linear relationship between flow Q and for lift. So one thing I just want to point out here is that this delta P is going to be across the whole system. And if we just assume that there's not much loss from the pipes, then really delta P will be only across this valve here. You will have this P naught and this P1. So we're going to have to go ahead and figure out how to correlate that pressure drop. That pressure drop will be equal to PV in this case. Otherwise, we'll do some other stuff. So let's go ahead. I'm going to get rid of that screen draw. So let's go ahead. Let's look at now. We have this relationship that's already given to us. Q, which is our flow rate, is equal to CV. CV is the valve constant times FL times the square root of the delta P, the delta pressure, over the specific gravity. And we have two different functions. We have one which is this lift function, which is R to the L minus 1, and the other one which is R equals 20. And then both of those will be multiplied at 20 times, how can I say? So we have one, this one, the other one's right here. So with R, I was trying to figure out why I said this was two ones. Right here we have this function. This is an equal percentage lift function with this R constant set by whatever valve it is. So in this case, our valve is equal to 20, and we have our lift from 0 to 1. So 20 raised to the whatever lift is minus 1 is our lift. And then the other one has a lift of some value between 0 and 1, straight up. So the first thing we'll do is we'll create linear and equal percentage lift functions, and then we'll plot flow as a function of lift. So to do that, we're gonna get some practice creating functions on the fly rather than down below. So the way we do that is we say the function name is equal to, we use this @ symbol to start showing that we're creating a function, an anonymous function actually, a lambda function it would be called in Python. And here we have the inputs and then the outputs afterward. So for example, with F linear, our input is L and our output is L. And that makes sense, but we just want some function to do that. And same thing with equal percentage. Our function input is L and the output is 20 raised to the, and it's element wise if we pass a vector, L minus 1. And I usually try to shy away from L's and 1's and the same thing, but there you go. So we're going to do a lift where we have 101 points between 0 and 1. And we're going to account for all these different lift percentages from fully open to fully closed. And we'll look at how the flow changes based on this equation we have right here. We have CV, F, L, and the delta pressure as inputs to this flow equation we're now creating. And flow, Q, if you look up here, is equal to CV times this flow function, and that's generic, so whatever we put in as F is going to be the function. It needs to just have the input L, times the square root of the delta pressure minus or divided by 1.1. So we hard code in that specific gravity. Then we know our delta pressure is equal to 100 bar, and our CV is equal to 2, so we can do this function for both. We can store results in flow linear and flow equal percentage, where flow will take lift, or which is this lim space from 0 to 1. We have here, this is the linear function, here's the equal percentage function, and then our valve constant and our delta pressure. So we're just creating a function that does it for us, and we're using this function which refers to one of these functions, if that makes sense. One of the functions is an argument within this function. we can go ahead and plot it. The idea behind here is hopefully we're not repeating work. Hopefully we can use these functions for both sections. So here we have our result. Go ahead and we'll run it just to make sure everything's the same. On the y-axis, and I notice we don't have that, so let's do y label, and that's flow. That's the result. Y label. Go ahead and run the section one more time. There we go. So we have flow on the y-axis, fractional lift on the x-axis. You'll notice 1 goes from 0 to 1, or from 0 to 1 is our input, it's our lift. The output is the flow. And so if we're regulating flow, you can see here the equal percentage flow is this dashed line. Linear flow is the straight line. And there we have our changes. One thing that's nice about linear systems is that we're able to control with the linear interfaces such as a PID controller that assumes that a linear change in error would result in a linear change in the response variable, or our manipulated variable, is that actually holds here. We have a linear relationship with the change in fractional lift, for example, and the change in flow. An equal percentage valve, we can look at the lecture video to learn more about those as well. So let's move on now to the installed valve that's installed within a system. So pressure drop across this system without the valve follows the following correlation between pressure drop within the system and Q. So we have some pressure drop which is proportional to 2 times Q squared. That's what the pressure drop is. So we'll plot this relationship between Q and valve lift L for the system and valve with CV is equal to 2. And so let's think about this one more time. I'll get out my handy dandy drawer and switch it to pen. So our delta P is going to be P naught right here. This is P1. This is going to be P2. And our delta P is equal to P naught minus P2. We have some pressure drop. That's what valves do. And so we have the same correlations for lift in our valves. We just want to remember that the delta P of the pump is equal to the delta P of the valve and of the system. So both of these are going to add together to create the delta P total. When our delta P pump is equal to 100 as before, and then we're going to go ahead and we're going to solve for the delta P of our valve here. And I'm going to go ahead and just do it along with us, just so we hopefully get what's going on. If I go like this, it'll give me some room. So let's discuss what's going on, how we solve this for delta P. I go ahead and just use my screen, save some time. So if we have this function, we'll go ahead and start here. The first thing I would do if we're solving for delta PV is just go Q over CV. I'll just go F, but we know that's F is a function of L, is equal to the square root of P delta PV specific gravity. Then if we square both sides, we have Q squared over CV squared. That's the lift squared. Should be better than that. 2 should be better as well. Is equal to delta PV GS. Now we can pull the squared out and just make everything a little bit easier. So delta PV is equal to GS, that's multiplied from the denominator over there, times Q over CVF squared. We have that right there. So that's how we would get that relationship. Just thought that'd be helpful to derive. So we have the delta PV of the valve and of the system. So if we add those two together, we get 100 is equal to that right there. So now we can change either, there's 2 things we don't know, or 2 things which may vary. The first is this FL, the lift, and if we vary the lift, we can look at the response Q, or we can change the flow rate and we can see how that affects our lift, what lift would give us whatever flow rate. So let's go ahead, let's obtain flow as a function of lift for the system. So we're going to go ahead, let's do that again. I'm just going to create some more space. let's not even look at that. Let's go ahead, use our pen. We have this system right here. I don't think it's too hard to say that we can go to start 100 minus 2q squared is equal to GS Q over CV F of L. Actually, I apologize. I was thinking of this wrong. We don't want to solve. We want to solve. Keep this. We want just Q by itself. So we solve for some function where F of L is the input and Q is the output. So the way I see this, let's go ahead. I'm going to get out my pen one last time. We want some function. I'll say this. Some function of lift is equal to Q. So the way I think of it is I try to factor out Q whenever we do something like this. And we know that this squared will distribute, in this case, to both the numerator and the denominator. So what we really have is 100 is equal to GS Q squared over CV squared F squared plus 2Q squared. So if we were to factor out and make this a function of Q squared, we would get GS over CV squared F squared plus 2. And that would be equal to 100. So we go ahead, we can divide that over then. So 100 divided by, and then we can just, I'll just go ahead and I'll just distribute, not going to say, well, let's go ahead, I'll just go like this. The nice thing about doing this in code is that we can just have that quantity without actually having to distribute. So CV squared, F squared, I apologize for my mouse handwriting, is equal to Q squared. And finally, to get Q, we take the derivative of both sides, or not the derivative, the square root. These two cancel. We get Q is equal to the square root of this right here. Let's look and see how that compares. Q, as a function of L, is equal to 100, and you can see that we have the numerator and the denominator that are distributed because we can do that. And the one last thing I should say is that when we had this this numerator, the denominator, we multiplied the numerator by the denominator to get this form. So now we have our two functions, our F linear and an equal percentage. We'll go ahead and plug these in where we have our change in pressure for our system. Both of those give us our Q's. We have our constants, and now we have our flow. Our flow is Q, which is a function of L and F. We use F as well so that we get we can specify which valve function we want to use. Then we do the square root of CV dot times FL. That's because if we pass a vector, we want to get these operations happening on each element-wise operations. All of that is squared times delta P divided by GS plus CV times FL squared times CV. This function right here. Then we have our linear flow, equal percentage flow, and we can plug those in. So you can see here, we have first flow. Flow is the same as before. We have flow, which in the system, we have an equal percentage flow, and then we have a desired profile. That desired profile goes from 0 to, let's actually just look at our graph to make sure, 0 to 6.5. We would want that to be as linear as possible so that some change in our fractional lift corresponded to the linear change of the system. So that's where you can see this linear flow. It was handy when we were looking at the flow through the valve, but when we're looking at the linear flow through the system, it doesn't quite do the same thing. This equal percentage flow, on the other hand, looks much more attractive now. If we look at the delta P through the system of both of these, you can see on the x-axis we're looking at fractional lift, and you can see each one is a different valve. So up here we have our linear valve, and down here we have our process equipment. The fractional lift point is we're looking at where the change in pressure of the process equipment and the valve would equal one another. And we can see that fractional lift point where they would equal one another. So the main point here, as far as we decide between the two, is looking at first the initial part one. It would seem that a linear flow system would be better for us. But remember, our flow really depends on our pressure difference. So if we're in an uninstalled system, a system, if we look at our first portion, that just has the valve itself, a linear valve might make sense for our control system. If we look at our, went too far. If we look at an installed system, and we look at our desired profile where we have a linear profile from top to bottom, the best thing would probably be our equal percentage flow pump, or a valve, I should say. Let me know if you have any questions. Hopefully this was a good exercise in seeing how these pumps work and relate to our control systems.